Hi everyone, this is section 6.3, Solutions of Polynomial Equations. In this lesson, we're going to solve polynomial equations using factoring and the root method. We're going to find factors, zero, x-intercepts, and solutions of polynomials. We're going to estimate some solutions with our calculator again, and then we'll solve polynomial equations with our calculator using the intersection and x-intercept methods. So a little bit of review before we start this lesson. Solutions of a polynomial. If f of x is a polynomial and c is a real number, then the following statements are equivalent. And we saw this theorem before. If a c value, whatever that is a 0, then we also say that is a solution or a root if we set that equation equal to 0. We're also going to see it as an x-intercept on the graph, and we say that x minus c is a factor. So for example, if you look at this picture down to the right here, we have this x-intercept at c. So c is called a 0, a solution or a root if we set our equation equal to 0, and then we would say that x minus c is a factor. So we're going to be using this theorem quite a bit. We're going to be using it first in solving polynomials that are in factored form. So if we're looking for a solution or a root or any of those other terms, we set it equal to 0. It's a fancy way of saying find the x-intercepts, which we did x-intercepts a while ago. That is when our y is equal to 0. Now, if the equation is already in factored form, like this first one, you're set to use the zero product property, where you just set each factor equal to 0. Now, 3 technically is a factor. If I set it equal to 0, I just get this false statement, so I get no solutions. You'll only get a solution if your common factor out front has a variable in it, something to solve for. If I set x minus 1 equal to 0, I'll get x equals 1 as a solution. If I set x plus 2 equal to 0, I'll get x equals negative 2 as a solution. And if I set x minus 4 equal to 0, I'll get x equals 4 as a solution. So we have 3 solutions to this polynomial: 1, negative 2, and 4. Looking to the next problem, again, I'm going to set it equal to 0 to start. So 0 equals negative 2x, x plus 5 squared, and x minus 3. So I'm going to set each of my factors equal to 0. I'll just go ahead and do that for all of them here first. And now I'm going to solve for x. In the first one, when I solve for x, I'm just going to divide by negative 2 on each side. I'll get x is 0. In the second one, if I move the 5 to the other side, I'll get x equals negative 5. And in the final factor here, if I set it equal to 0 and move the 3 over, I'm going to get x equals 3. So my solutions here are 0, negative 5, and 3. Now, one thing we want to make a note of here is negative 5 is actually a solution that occurs twice. So we're going to say that it has a multiplicity of 2 because that factor was squared in the original equation. So that's going to help us later on when we do some things with graphing. When you type it in your MyMathLab, you can just type it in once, but know that the solution occurs twice. Next, we can solve by factoring. So solving by factoring, this is just going to be review from, again, a previous lesson. We're going to set it equal to 0. And then the first thing we're going to look for in any of our factoring problems is, do any of these terms have something in common, a common monomial factor that I could divide out? And all 3 of these terms in the first problem have an x squared in common. If I divide x squared out of every term, or undistribute it, that would leave me with x squared minus 2x minus 3. And now what remains is a trinomial with an a value equal to 1, meaning there's no number that I see in front of my x squared. Those problems can be factored by setting up 2 sets of parentheses, a variable in the front of each, and here we're looking for 2 numbers that multiply to the last term and add to the middle term. So what multiplies to negative 3 and adds to negative 2 is negative 3 and positive 1. And now your factor, so it's going to be just like the problems on the previous page. We're going to set each of our factors equal to 0. And from there, I'm going to solve on the first one. If I take the square root of both sides, I'm going to get just x equals 0. In the second one, I can move my 3 over, and I'll get x equals 3. And in the final one, if I move my 1 over, I'm going to get x equals -1. So my solutions to this polynomial are 0, 3, and -1. And we say that 0 has a multiplicity of 2, again, because that variable or that factor was squared in the original problem. All right, for our next problem, we're going to start the same way. We're going to set our equation equal to 0. And then we're going to factor out what they have in common. These two terms both have a 2 as a factor and an x. If I divide the first term by 2x, I'll be left with x squared. And if I divide the second term by 2x, I'm left with -9. I can factor this a little bit further now. When you have two terms that are perfect squares with a minus between them, that's difference of squares, and it's going to factor to the same parentheses, 1 plus, 1 minus, so conjugates. The square root of x squared, or what times itself gives me x squared, is x. What times itself gives me 9, 3, and 3. And you can always check this by foiling if you want. So now we're ready to set each of our factors equal to 0. And now we can solve for each of our variables. In the first pair, I can just divide by 2 on each side and get x equals 0. In the next set, I can move the 3 over, and it becomes x equals -3. And in the last one, I can move the 3 over, and it becomes x equals +3. So my solutions are 0, -3, and +3. And each of these factors that these numbers came from occurred once. So I don't have anything with a multiplicity higher than 1 as a solution here. Next, we're going to review factoring by grouping. Again, I'm going to start by setting my equation equal to 0. To factor by grouping, you're going to pair up your problems 2 and 2. So usually, we know that we have to use grouping because all 4 of our terms don't have anything in common, and there's 4 terms, so I can pair them up 2 and 2. In the first pair, I'm going to factor out what they have in common. These have a 2 and an x squared in common. And that leaves me with x plus, oops, sorry, not x, 6x. Let me catch that before we go too far here. There we go. 6x plus, and then if I factored everything out of a term, there's still a 1 there. So you can double check that by just distributing. You want to make sure there's something there that if I distribute that x squared back in, I'm left with what I started with. The next pair of terms have a -5 in common. And that again leaves me with 6x plus 1. And that's the key to grouping, that you get that same parentheses twice. So now we can write this in a condensed form. 0 equals 2x squared minus 5, the two things that I factored out, times 6 plus 1. And if you want to check at this point, you can FOIL, and you should be right back where you started. Now I'm going to set each of my factors equal to 0 and solve. I'm going to start with the one on the right. If I move the 1 over, I have -1, and divide by 6, I have -1/6. On the one on the left, I'm going to add 5, divide by 2, and this looks like what we did before was solving with square roots. And then I'm going to take the square root of both sides. So x equals, if I take the square root, I need to include a plus or minus, square root of 5 over 2. So really we have 3 answers here, -1/6, positive square root 5 over 2, and negative square root 5 over 2. Let's try the next grouping problem. Again, I'm going to start by setting it equal to 0. And I'm not going to actually rewrite the whole thing here. You get the idea. I'm just going to start pairing them up and factoring out what they have in common. 49x cubed and 35x squared have a 7 and an x squared in common. If I divide that out of the first term, I'm left with 7x. And if I divide that out of the second term, I'm left with negative 5. The next pair of terms, keep in mind, if you're not sure what to divide out, we want to be left with 7x minus 5. So that kind of gives you a clue about what you should be dividing out if you're not sure. I should be dividing out a positive 8. We'll make that happen. So now I'm going to set each of my factors in our condensed form here. 7x minus 5, the parentheses I was left with both times, and then the two things that I factored out. 7x squared plus 8. Setting each of my factors equal to 0 now, I can solve. Again, I'm going to start with the one on the right, my linear equation. I'm going to add 5 and divide by 7. I get 5/7. The one on the left, I'm going to subtract 8, divide by 7, and then if I take the square root of both sides at this point, I'm taking the square root of a negative. And remember, that gave us no solution before we saw that special case. So I'm not going to get any solutions from that factor, meaning my only answer to this equation is x equals 5/7. Okay, here are a few solving by factoring problems for you to try. If you want to try to solve all of them, and then if you have a moment, you can check your answer. If something is a solution, remember it's going to make our equation equal to 0. So we didn't do any of our problems on the previous pages, but if you want to, you can plug equations or numbers back into your equation and see if it gives you 0 to confirm an answer. All right, let's start with the first one. If I set this equal to 0, I see that I have 4 terms, and all 4 terms have nothing in common, so I'm going to solve by grouping. First 2 and the second 2. In the first pair, I can take out an x squared, and that leaves me with 2x minus 3. In the second pair, I can take out a positive 2, and that also leaves me with 2x minus 3. From here, I can write it in condensed form, x squared plus 2, 2x minus 3, and then I can set my factors equal to 0. If I solve for x squared, I'd have to subtract 2 first. And then if I take the square root of both sides, again, I would be taking the square root of a negative like we saw on the last page. So that piece is going to give me no solution. Now the one on the right, add 3, divide by 2, and that is the only solution to this equation. Looking at the problem on the top right now, these two terms have a common factor of 4x squared. If I take 4x squared out of the first term, I'm left with x squared. And if I take 4x squared out of the second term, I'm left with minus 4. I am now left with difference of squares. So I'm going to set up my 2 parentheses. I know it's going to factor to the same pair of numbers, 1 plus, 1 minus. X and x give me an x squared. 2 and 2 give me a 4. And now I'm going to set each of my factors equal to 0. I'm going to divide by 4, which will still just give me a 0, and then take the square root, x equals 0. I'll also get from the other two, negative 2 and positive 2. So my solutions are 0, negative 2, and positive 2, and just make a note to yourself that 0 has a multiplicity of 2 because that x was squared in that factor, so technically it occurs as a solution twice. And then I saved the easiest one for last for you guys here. This one's already in factored form. If I set it equal to 0, I just need to set each factor equal to 0. you should get 0, 2, and -5. And again, just make a note, -5 has a multiplicity of 2 because that factor occurred twice, and therefore the solution occurred twice in that equation. Okay, so the next thing we're going to talk about is solving with the root method, which is similar to solving with square roots. We're just going to extend it now into larger roots, cube roots, fourth roots, that sort of thing. So you want to maybe look for factoring possibilities first. If you cannot factor, then you can solve using the root method, or it might be a little bit of both in some of these problems. But just like the other ones, we're going to set it equal to 0 to start. So I'm going to replace my f of x with a 0. Both of these terms have a 3 and an x squared in common. If I take 3x squared out of both terms, I'm left with x squared minus 3. And now I can set each factor equal to 0. So we've kind of already done this in some of our grouping problems already. I'm going to divide by 3, which gives me 0, and I get x is 0. On the other side, I'm going to add 3, which gives me 3. And then because I have a squared, a power of 2, I'm going to take the square root of both sides. Square root, square root. If you are taking an even root, so a square root, a fourth root, a sixth root, an eighth root, any even root, we're going to include a plus or minus in front of our answer when we take that root. So plus and minus, square root 3 does not simplify that radical, so we're just going to leave it square root 3. So our answers are 0, positive square root 3, and negative square root 3. And again, just make a note, 0 has a multiplicity of 2 because that x was squared. Looking at the next function on the right, I'm going to set it equal to 0 to start. And this one does have a 3 in common between these two terms, but it's not really going to help me with this x cubed. I'm not going to be able to factor an x out. So you could factor a 3 out. Let's call that optional, but we don't need to in this problem. All we're going to try to do is get whatever our variable to the power is alone. So here I would add 81 and then divide by 3. So that'll give me x cubed equals 27. As soon as you have isolated the variable to the power, you're ready to do your root. Now this time I have a third power, so we're going to do, if I can squeeze it in here, a cube root on both sides. If you have an odd root, so cube root, fifth root, seventh root, etc., we do not include a plus or minus. There will only be one solution. X equals cube root of 27 is just 3. And that is our only solution to this equation, x equals 3. Looking at the final one at the bottom here. Again, these two terms I can maybe factor a half out, but there's no variable they have in common, so I'm not going to do that. We'll just skip that step and go straight to trying to get that x to the fourth power alone. I'm going to add 8. And then at this point, you could divide by a half, but usually we don't divide by fractions. We multiply by their reciprocal. So I'm going to multiply by 2 over 1 on both sides. And that'll give me x to the fourth equals 16. And now I'm ready to take my root. This time I have a fourth power, so I'm going to do a fourth root on each side. Because that is an even root, I will put a plus or minus in front of my answer. Now in your calculator, fourth root of 16, you can find the root function under math, or you could just type in 16 to the 1/4 power. Remember, that's equivalent to seeing a root. We can type it in as 1 over that power. Either way, you're going to get a 2, and we put a plus or minus in front of it, and because it's an even root. So x equals 2 and x equals -2 are our two solutions to this equation. Okay, in the next problem we're going to solve with technology. So I'm going to bring my calculator up here. Okay, so remember we're setting our equation equal to 0. If we see something kind of nasty like this where there's a lot of terms, they don't have anything in common, even if I factored by grouping here, I wouldn't end up with that same parentheses twice remaining. So we solve problems like this that become a little more complicated with technology. Once I set it equal to 0, you can solve using the intersection method or the 0 method. I personally think the 0 method, or your book calls it the x-intercept method, is the easiest with polynomials. So I want everybody to go into y equals in their calculator. We've got all this stuff from the last lesson in there, so let's clear that out. We're going to clear out our y equals, and we're going to turn our plot off. There we go. And we're just going to type this equation in. 2x to the third plus 5x squared minus 4x minus 3. And then I want you to hit zoom 6 because we were in some weird windows for our statistics. Zoom 6 will just set you back to your standard window. Now we're looking for solutions here. Solutions, remember, another word for those are x-intercepts or zeros. So to calculate those, we're going to hit second trace, and we're going to choose 0, number 2. This is the x-intercept method that we've done before. So I'm going to go from left to right. There are 3 places where this graph is intersecting the x-axis. So I'm going to have to do this procedure 3 times. The first place it looks like it's intersecting is around -3. So for my left bound and right bound, I'm going to use -4 and -2, just numbers on the either side of it. Oop, I think I did something wrong there. Hold on. Left bound, -4, right bound, -2. There we go. And you should see those vertical lines on either side of the intercept that you're trying to calculate. And then when it says guess, just hit enter. And what is going on with my calculator here? 0, left bound -4, right bound -2, and guess. Okay, so let's look at solving with technology. For this problem, we're going to start by setting it equal to 0. And then you'll notice that this one would be difficult to solve with factoring. All 4 terms don't have anything in common, and even if I tried to factor by grouping, I wouldn't be left with that same parentheses twice. So what we're going to do is we're going to type this equation in y equals. If you have stuff from the previous lesson in there, you just want to clear that out. You also want to make sure that your plot is not highlighted like mine. If your plot is highlighted, just go up to plot, hit enter, go back down. And then remember, we were in some weird windows before with our statistics, so we're going to hit zoom 6 to reset back to our normal window. And then here's the graph of our polynomial. When we're solving, remember we're looking for solutions or roots, or x-intercepts is really what we want to focus on if we have a graph. And you can see there are 3 places it looks like where this graph is crossing the x-axis. So we're going to repeat the same procedure 3 times. This is the x-intercept method that we're using. We're not going to practice the intersection method because I think that's a little more difficult with polynomials. But you can use that method as well that we've talked about in previous lessons. If you see instructions about solving with technology, you can use either method and its equivalent. So we're going to hit second trace, and we're going to choose 0, number 2. The first one I want to calculate, it looks like it's at -3. So I'm going to choose, oh, I overshot it there, right there is what I'm going to try to calculate. So if it looks like it's about -3, my left bound I'm going to say -3.5, just a number to the left of it. And my right bound I'm going to say -2.5, a number to the right of it. And then guess, and then there's my first answer, -3, 0. So -3 is my first solution. We're just going to repeat the process 2 more times. Second, trace, 0 is number 2. And then the next x-intercept looks like it's occurring about -0.5. If I go down a little bit. So I'm going to say my left bound is -1 and my right bound is 0. Just a number on either side of it, fairly close. Guess? And it is at -1/2. So that is my second solution. And we're going to do it one more time. Second, trace, 0, number 2. And then the last one looks like it's occurring at about 1. So I'm going to say left bound, -0.5. Oh, sorry, I don't want to do that. I want +0.5. Let's try that again. Just start it over there. So left bound, +0.5. Right bound, let's make it 1.5. And that's got it on either side. That's good. And guess, and I do have a 0 at 1. So that is my third and final solution. So your answers here are, I'll just circle them all that we found in the calculator, -3, -0.5, and 1. And we can see those all in the graph. Any of the problems that we've done already where we solve by factoring or with roots, this is a great way to check your answers. If you type your equation in y equals, even if you don't calculate the zeros, you can just look at the graph very quickly and see if you have x-intercepts at the values that you found. If you have x-intercepts approximately at the values you found, it's a quick and easy way to check that your solution is right. Or again, remember, you can plug the numbers back into the equation and make sure they give you 0. All right, moving on. Here are a couple problems for you to solve. For number 1, I want you to solve using the root method. For number 2, I want you to solve with technology. Okay, for number 1, I'm going to set it equal to 0. And I just have one variable here, so I'm just going to try to isolate that. I'm going to add 16. I'm going to divide by 2. And then because I have an x to the 3rd power, I want to use a cube root to cancel that. So cube root of x cubed just gives me x. Cube root of 8, that's a perfect cube, but you can type it in your calculator, 8 to the 1/3 power, or use the cube root function under math, and it's going to give you 2. You do not put a plus or minus in front of this answer because it is an odd root. Only even roots do we include a plus and minus, so your only solution is 2. The next problem, let's go through in the calculator together, just to refresh. You can check your answers. So I'm going to go to y equals. I'm going to clear out what I've got there, and it is 2x to the 3rd plus 3x squared. Let's see what else we've got here. Minus 6x minus 8. And then I'm going to hit graph. And again, it looks like I've got 3 intercepts that I'm going to calculate. So we're going to hit second trace, 0, number 2. The first one looks like it's approximately at -2. So I'm going to use left bound, -2.5, right bound, -1.5, and then guess. And it gives me -2 as my first solution. Drag that over. Okay, let's do it again. Second trace, 0, number 2. The next one looks like it's about at -1. So left bound, I'm going to use -1.5. Right bound, I'm going to use -0.5. And then guess. And this one we're going to have to round. It is an irrational number, it looks like. So I would say if you round to 3 decimal places, -1.186. If you rounded to 2 decimal places, -1.19 would be a solution. And then let's do it one more time for that last 0 on the right. Second trace, number 2 for 0. This one looks like it's somewhere between 1 and 2. So I'm just going to choose left bound 1, right bound 2, and guess, and I get about 1.686. We'll drag that guy down and add it to our list. So 3 solutions here are -2, -1.186, and 1.686. Okay, in the next problems, we're going to work backwards. We have the equation, we have the graph, and we want to find the factorization, which is a fancy way of saying we want to find the factored form of this equation. So we're going to focus in on where we have x-intercepts at. Here, here, and here. And we're going to use those to help us a little bit. So it looks like, you know what, I don't love, this problem. Okay, in the next couple problems, we're going to find the factorization. We're going to cross out this first problem that's on here. This one's going to be pretty difficult, I think. I'm going to second guess myself here, but I think that one's going to be a little difficult to do by hand. So we're going to take that one out. We're going to do the one on the right together here, and then we'll do another one on the next page together as well. To find a factorization, we have the equation, we have the graph, but what we don't have is the factored form, and that's really what we're looking for here. So to find the factored form, you're going to focus in on the solutions or the zeros or the x-intercepts, most importantly where it's crossing the x-axis. And I'm going to list out what those are. I have solutions at -5, -3, and at +2. Now, +2 is special, you'll notice, because we're not going through the x-axis at those points, we're turning around. And if you remember from a previous lesson, that means that you have a multiplicity of 2. So that means when we put this back in factored form, we need to make sure that that factor occurs twice. So my factored form, our theorem at the very beginning of this lesson said that if c is a 0, that x minus c is a factor. So what we're going to do is we're going to put x minus in front of each of these values. X minus -5, x minus -3, and x minus 2, and that one, remember, occurs twice. So we can either write it twice or just say squared. If you have minus and negative, you're going to change that to a plus. And then if you're wondering kind of why we do that, imagine solving this equation. If I gave you this equation in factored form and said solve, you would set each of these factors equal to 0, and you would get out as solutions -5, -3, and +2. So just working backwards when we put that x minus in front of it. Now the only thing we're missing here is the leading coefficient, and this is function g of x, by the way, so I'm going to put it equal to g of x. The leading coefficient is the number that's in front of your leading term. And your leading term is the one that has the largest exponent. So this one's written a little out of order, but my leading term in this polynomial is 2x to the 4th. The 2 in front is your leading coefficient. So we also include that 2 there. Now, if you wanted to check that this matches this equation, you could either graph both of these equations and see that they look the same, or you could just graph the bottom equation and make sure that your ends were going in the same direction and that you were crossing the x-axis in the locations and the way that you see them in this picture. So let's do one more of these together. I know this next page says practice, but we're going to do the one on the left together here before you guys try the one on the right. So again, we have the equation, we have the graph, we want to work backwards and find the factored form. So let's focus in on those intercepts here, here, and here. And it looks like those are occurring at -1.5, +1.5, and we're just approximating these the best we can, and then at 0. So, and 0, by the way, we're turning around at that point, so we're going to say that that guy has a multiplicity of 2. Putting them back in the factors, remember putting x minus in front of each thing, x minus -1.5, x minus 1.5, and then x minus 0 occurs twice. Leading coefficient in this polynomial, my highest power here again is a 4. There's a 1 in front of it, so we can put a 1 out front. This polynomial approximately factors to x minus 0 squared, which is just a fancy way of saying x squared, x plus 1.5, and x minus 1.5. Now, again, if you want to check this, you can graph your answer here and see that you're approximately crossing in the same locations as this picture, and you have a 0 at the location of 0 that turns around and does not go through the x-axis. Okay, I want you guys to try this last one. So see if you can put this polynomial in factored form. Remember, you're going to focus in on the x-intercepts. If an x-intercept is turning around at that point, it has a multiplicity of 2. If it's going through the point, it has a multiplicity of 1. Okay, so here we have zeros at -4. Looks like -3, and both of those have a multiplicity of 2 because they're turning around, and then at x equals 2. The leading coefficient in this polynomial is the one in front of my x to the 5th power because that's my highest term. So I'm going to say h of x equals 1/2 for the leading coefficient. X minus -4, or you could just say x plus 4. And that has a multiplicity of 2, so we square it. X minus -3, or you could just say x plus 3. Again, it has a multiplicity of 2, so you square it. And then finally, x minus 2. And that went through the x-axis, so that has a multiplicity of 1. We don't need to square that parentheses. So this is your factored form. If you want to check it, you can graph that in the calculator and see if your graph looks approximately the same. Okay, our last few problems are application problems that you're going to see in your MyMathLab homework. In the first problem, this is revenue. The revenue from the sale of a product is given by the following function. Use factoring and the root method to find the number of units that must be sold to give a 0 revenue. So that's important here. 0 revenue, we want our revenue to be equal to 0. So we're solving this equation for x. So the first thing that I'm going to look for here is I definitely have things that these terms have in common. I at least have an x that I can see that they have in common. So I'm going to take an x out of both. And I could probably factor a little bit more with the decimal, but sometimes it's a little more difficult to see, so we're just going to leave that in there. 0.003, and I'll just be left with an x there. And now I can set both of my factors equal to 0. If I set my first factor x equal to 0, that's my first answer, 0. If I set my second factor equal to 0, I'm going to subtract 12,000, which would give me negative 12,000. And then I'm going to divide both sides by that negative 0.003. So you'll need to do that kind of off to the side in your calculator. Negative 12,000 divided by negative 0.003. And I get 4 million. 4 with 6 zeros at the end of it. Okay, and then if I wanted to label these, it said find the number of units. So either 0 units or 4 million units will give me that solution, a 0 revenue. Does the graph of this revenue function verify the solution? Well, let's find out. So we're going to go into our y equals. We're just really checking by graphing here. Clear that out. I'm going to put my equation in. 12,000x minus 0.003x squared. Now, if I use Zoom 6, I'm probably not going to see anything because remember, we're looking for a solution at 4 million. That's an x-intercept at 4 million. So I'm going to change my window. I'm going to make my x min negative 10, sure, and then my x max, I'm going to make it 5 million. There we go. An x scale, I'll make it 1 million. The y's are not super important here. As long as you have a y value of 0 within this range, you'll be able to see your x-intercepts. That's the part that we're focusing on. Hit graph. And then you can see here, I'm crossing at 0. It's a little hard to see, but it's in blue there on the left. And then at the fourth one over, so at 4 million, we also have an x-intercept, which you could calculate if you want to. But does the graph confirm it? Our answer is yes. So if you don't see it with the graph, maybe play with that window a little bit and see if that helps. All right, let's try another application problem. This one's about cost. The total cost of producing a product is given by the function c of x equals x to the third minus 12x squared plus 3x plus 9, $1,000, where x is a number of hundreds of units produced. Okay, so I'm going to maybe write or underline that. That's important. So thousands of dollars is the y, or the cost, and x is the number of hundreds of units produced. So if x is 1, that's 100 units produced. How many units must be produced to give a total cost of $45,000? Now remember, y is in thousands of dollars, or c of x is in thousands of dollars. So if I want to represent 45,000, that means my y, or my c of x, is just 45. 45 means $45,000 in this equation. So I'm going to say 45 equals all of this, and now we're solving. So the first thing that I'm going to do is, remember, we got to get it equal to 0. So I'm going to take that 45 and I'm going to subtract it on both sides. So 0 equals x to the third minus 12x squared plus 3x minus 36. I have 4 terms. Looks like all 4 don't have anything in common, but this looks like a good candidate for grouping. So I'm going to pair up 2 and 2. First, I'm going to look for what these terms have in common. The first 2 have an x squared in common, leaves me with x minus 12. The second 2 have a 3 in common, also leaves me with x minus 12. So now I know, because I got that same parentheses twice, I can factor by grouping. I'm going to set my equation into the condensed form. X squared plus 3, the 2 things that I factored out, go in one parentheses, and x minus 12, the parentheses that was left, goes in the other. Set each factor equal to 0. X squared equals, if I move the 3 over, negative 3. I can't take the square root of a negative, so that gives us no solution. For the other one, if I move 12 over, I get 12. So remember, x represented number of hundreds of units produced. So if we get 12, that actually means 1,200, add 2 zeros to the end of it, units are how many need to be sold to give me a cost of $45,000. So if you're getting something wrong in my math lab, a problem like this, make sure you're really careful about what those variables represent. It could be as easy as taking a couple zeros off or adding a couple zeros on as you're solving, to make sure you account for what they're using to represent each of our x and y's. Okay, next we're going to look at an investment problem. Here, the future value of $10,000 invested for 4 years at an interest rate compounded annually is given by the following equation. Find the rate R as a percent that will give a future value of $14,641. So S in this equation is the future value. So we're going to make S equal to 14,641. That's how we're going to start. Now I could make this equal to 0 to start, but I have one variable here and I have a power. This is a good candidate for roots anytime you have these investment problems. To solve with roots, remember whatever's taken to the power, so the parentheses here, we need to get a loan. So I'm going to first divide both sides by 10,000. That's going to give me 1.4641. equals 1 plus r to the 4th. Now, don't try to use exponent rules here. We cannot distribute the 4 through. That's a common mistake because we have a plus there. That only works if it's division or multiplication. So because we have the parentheses isolated and because that parentheses is to a power, we're all set here to take my root. And I'm going to use a 4th root because it's a 4th power. So on this side, I'm just going to be left with the 4 and the 4 will cancel, 1 plus r. On the other side, in my calculator, I'm going to do the 1.4641 to the 1/4 power is how I'm going to type it in. You could also use the fourth root in your calculator. And it gives me exactly 1.1. Technically, because this is an even root, we would put a plus or minus in front of it. But because we're talking real life applications here and we're solving for R, which is an interest rate, we can't have a negative interest rate, so we're not going to include the negative solution. To finish solving now, I'm just going to subtract 1 on each side, so I get 0.1 equals R. Now our answer needs to be R as a percent, so we need to take our decimal and write it as a percentage. To write a decimal as a percentage, you just move the decimal place 2 spaces to the right. So this is 10% is my interest rate. That will give me that future value. Okay, our final problem today is a volume application. Here we have a box that's going to be formed by cutting a square X inches from the corner of a rectangular piece of cardboard, and the cardboard is 24 by 18, and I've drawn a little picture here for you. So it's 24 across, it's 18 up and down, and then each little square that's getting cut out is X by X. Okay. And then we're going to fold up the sides. So if you can imagine if those little black squares were gone, what I would be left with, if I folded here, 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 and here, I would have 4 flaps that I could fold upward, and I'd be left with a box that did not have a lid on it. So an open box is what we're creating here. We want to write a function that represents the volume of the box. So volume is length times width times height. And when you do this problem in my math lab, they might break this question down into several pieces. They might ask you find the height, find the length, find the width first, but we're going to do it all together at once here. So volume equals, let's start with length. We want the length of the box after it's been folded up. So that would be this guy, but take away the 2 squares. So if the original length was 24, and I took off 2 sides, little X's or squares that were X on each side, that length would be 24 minus 2x. The width would be similar. It would be this guy, take away an x on each side. So it would be 18 minus 2x. And then finally, the height would be how high the flaps go, which would be, in this case, whatever x is. And this is the volume in factored form. You could always do a lot of foiling here if you wanted to, but I would just leave it in the factored form. Find the values of x that make the volume equal to 0. So I want my volume to be equal to 0. And because it's already in factored form for us, this is going to be really nice and easy. I'm just going to set each factor equal to 0. So 24 minus 2x equals 0. 18 minus 2x equals 0. And x equals 0. I'm going to do my work down here. To solve for x in the first equation, I'm going to subtract 24 and then divide by -2. So x is 12, and I would label it inches here. In the next one, 18 minus 2x equals 0. Subtract 18 and divide by -2, 9 inches. And then finally in that last one there, if x is 0 inches. So if I cut out a square of size 12 or 9 or 0, technically, that would make this volume equal to 0. So it says graph this function in a reasonable window. Think about what makes sense in the context of this situation. So let's go ahead and graph it, and we're just going to find that reasonable window. Let's clear out that and put our equation in. 24 minus 2x is my first factor. 18 minus 2x is my second factor. And then x is my last factor. Now it looks like the biggest solution I have is 12. So if I hit window, actually let's hit zoom 6 first and just see what that looks like. Okay, let's go back to window. Give me some regular numbers to start with. X values in this problem represent the size of a square that you could cut out. We cannot cut out a size square smaller than 0. So we're just going to start with an x value of 0. My x maximum, again, it looks like I had a value that went all the way up to 12, so let's make that 13. X scale is 1. Y in this problem represents volume. So again, I can't have a negative volume, so I'm going to start at 0. And the volume could get pretty large here, so maybe let's make it like 500. But we can always adjust that later if we think it's too high or too low to see the peak in the graph. So let's hit graph. And you can see I need to go a little bit higher on my y-axis. And let's also talk about the x-axis here. I'm seeing my x-intercepts at 0, 9, and 12. But between 9 and 12, it's actually going down, and it's going to give me a negative volume. So actually, anything after 9 is not a reasonable solution. So I'm going to change my x-axis just from 0 to 10. I'm also going to go back to my solutions here and get rid of 12, because that does not give me a reasonable answer. And here's why you can see that from the picture, if that's not making sense. Let's look at that side that's 18 in length. If I want to cut a square on both sides, I wouldn't have enough cardboard to cut squares that are 12 inches by 12 inches. The maximum that I could cut from each side, because that side is 18, is 9 and 9. So in the context of this situation, 9 is actually the largest square I could cut out and have enough cardboard to do so. And 0 is the smallest square that I could cut out and have enough cardboard to do so. So back to our window. Let's change that a little bit. So 500 for the volume, maybe let's make it like 800. And then my x max, I'm just going to take that up to 10. And hit graph. And there we see a much better picture of our answer. Finally, we want to determine the size of the square that will result in the maximum volume, and we want to figure out what that volume is. So once we have this great picture, we can just calculate the maximum. Second trace, we want maximum number 4, and we know the maximum occurs somewhere between 0 and 9. So I'm just going to use those for my left bound and right bound. 0, enter, 9, enter, enter again, and there is my maximum. I'm going to drag this over. There we go. So the x again represents the size of the square, the y represents the volume. So to answer this question at the bottom now, the square size that we could cut out would be about 3.4 inches. And that will result in a maximum volume of 600 and probably 55, if I round that, inches cubed, because this is volume. So the lowest square I can cut out is 0, the biggest square I can cut out is 9, and the square that will result in a maximum volume, so it'll maximize the volume of the box, if we want to say it that way, is 3.4 inches, and it's going to take me all the way up to 655 inches cubed of volume.